Okay, so I'll start. So welcome to this talk about configuration management primitives. We're here at configuration management camp, but you also may know that it may also be called YAML camp sometimes because we end up doing a lot of YAML. But today I don't want to talk about YAML camp. I'll try to go a level deeper, and so I welcome you to check apply camp. We'll see what we mean by that. So what is check apply? Check apply is basically a function that looks like this. So here it's Python, but it will check the state of something. If it's okay, it will do nothing, and if it's not okay, it will fix it. And that's actually the basis of a lot of infrastructure automation tools. And it's really the building block that allows idempotency for stuff that is not made for it. As you can see, the state is a global variable, and that's really how it works. It's only side effects on a global variable. And it's pretty much what all automation software is about when you look close enough. And in this talk, I'll try to talk about what's new in the check apply world, and we'll see if it's still relevant or if there are alternatives now. So briefly, I'm a system developer. I work at Rudder since 2015. I'm also a CF Engine contributor, and I used Ansible and Puppet over the years. So it's about configuration management primitives. I've talked about the check apply idea of checking if something is correct and fixing it only if necessary. But before digging into this topic, I want to start by talking a bit about the raw material that we actually manipulate when we are doing system automation. So what's actually the state we transform? So what's the raw material we use actually? So in our case, we don't use logs. It's mostly something we produce, but we don't use it. What do we use? Well, basically, software automation, system automation, and infrastructure automation in general is made of some configuration data about the state you want your infrastructure to be in, and some APIs that you will use to apply this state. And in the middle, you have a kind of check apply somewhere. So we interact with what I call system APIs, which are kind of programming interfaces. Sometimes it's a big word for something that's really hacky, but it's actually a programming interface. And it's always kind of a high-level interface. The low level of infra automation is still very high level in the operating system world. System automation is really about glue and not deep actions. Configuration data itself can be either a program or a data or a declarative using a DSL. It doesn't really matter for today's talk because at the lowest level, it doesn't change much. We have an expected state, we have a tool we can use, which is a system API, and then in between we will apply the state to the system. It doesn't change much. So for the next slides, we'll focus a bit more on the Linux context, Linux server context, and we'll see what system interface we actually use in automation on Linux systems. And for the most part, it's really it's Unix v7 actually, or stuff that existed there, or maybe something that we would actually call POSIX, but most of what we actually manage on the systems are actually using text interfaces, commands, maybe sometimes sockets, but that's pretty much all. So we still use kind of old interfaces. I've struck the C because using C APIs is difficult, so we often end up using commands and text interfaces for a lot of automation software. A bit has changed since the beginnings of, well, Unix 7 or even the beginnings of system automation, as systems have moved towards a more declarative type of data. For example, the init scripts were mostly replaced by systemd units, so we replaced the program by a data file. And most new server programs actually use data as source for their configuration, contrary to older software which often had a custom configuration language. So that makes system automation life a bit easier, but hasn't changed much apart from that. And we also have libraries like systemd, which allows interacting with the system in a more programming interface way and less hacky command parsing way. But yeah, all configuration management tools still run commands and parse the output using regexes to try to provide a nice interface for the users. It's the internals of automation software is often pretty messy. You'll see a nice, let's say, package management method in your configuration management tool. But if you look at the implementation, it will check the version of the package manager, and if it's older than this version, it will add another specific option which is necessary, except if it's this exact version that had a bug that was not for which the fix was not backported to Rails, so we have to make a workaround. And automation code is full of workarounds, and usually pretty messy because of this very unprecise interfaces. And as an addition, the configuration surface of a modern Linux system is huge. It really looks like this. So, for example, if you just look at the runtime stuff, a Linux kernel has a lot of configurable stuff that you can modify at runtime. So, and there is state everywhere on the system. Every program that runs has its own internal state. So, the actual configuration surface of an operating system is really huge. So, configuration management generally only manages a very small part of it. So, you will install a few packages, you will configure a few files, and you will say, okay, my system is managed. And for the rest, I don't know, probably it's in the default state. So if I took my image from a cloud provider, it's in the default state that was used when creating the image. It may be a problem because we don't actually know the whole configuration of the systems, but only the small parts that we configure. And containers may look like a solution to this, but I don't think they really are, because we freeze the state of at least of the disk and the software, but we don't actually know what there's inside, and we still take things from outside and ignore almost everything, all the parts that we don't configure. And to conclude with this introduction, I will say that maybe configuration management has failed on some levels, because the immutable infrastructure software usually dropped everything configuration management had built and started over from shell scripts. Docker files are usually pretty ugly shell scripts. So why wasn't the software we built kept in this context? Well, maybe because it was not good enough, maybe because it didn't bring enough value, but maybe we can do better. And maybe there is still room for improvement. So now we'll have a look at the solution space. So how we actually do configuration management now, and what we can do in the future. So what's configuration management? In the next slides, I'll describe it as an engine. So that's the core of the system that will read the expected configuration and apply it to the systems. And then you have resources which implement the different items you can configure, like packages, services, HTTP calls, anything. And we'll look more precisely at the resources level. And we'll see what are the choices we make when we implement resources now, what are the trade-offs, and what we can do better. So we'll start briefly with the engine. That's not the topic today, but that's the part of the application that will be generic over what we configure. It will just evaluate data, maybe make string substitution, iteration, and then call the resources with the parameters. It's kind of a big check apply with a structure that is often a stack, kind of a stack with some links maybe, with an exception that I know of, which is MGMT, which has a graph structure, which allows a lot of very interesting stuff. But for the most part, it's kind of a stack, so you take the first part of the policy, and then you take the first item in the first part, and then the second item, third item, and you will evaluate the policies like this. So let's start from our check apply. So that's still the same. And we'll see that we have a first choice to make, which is at which level we will make the limit between the engine and the resource. So does the resource decide on its own, or is the engine controlling everything? In this case, we let if we imagine that the check apply is implementing a resource, we give it quite a lot of room, because the resource is responsible for checking and applying, and make the decision between do I need to do something or not, and then doing it. But there's another way to do it. You could imagine that implementing a resource in your engine means implementing two functions, one check and one apply, and the engine is responsible for calling check, and then if it's not correct, calling apply. So that gives a very simple but first choice to make when you're designing the interface between configuration engine and the resources. We'll add another very simple feature, which is like dry run, audit, check. It has different names. It can be added really easily in a check apply function. You just add a new parameter, and then depending if your dry run value, your audit value is true or false, you will either, in case the system is not correct, you will either fail with an error or fix the system if it's not in dry run mode. So in this case, that's an additional parameter that the resource has to take into account. And it's pretty, it's implemented in most configuration management systems. Now we'll see something a bit more interesting that's not always implemented, which are all kinds of static checks. Because we can limit and precise what the resource expects. And it is in this example, I've added some switch to Rust. It doesn't change much. Add some braces, but it's also add some types in the function signature. And we can see that we take a directory resource. And in this case, we constrain the shape of what we take. That means that this resource will accept a path present, that means present or absent maybe, and a permissions structure that will contain, let's say, a Unix permission information. So in this case, we're able to know before calling it what the resource will expect, and we are able to validate the parameters and avoid calling it with invalid data. And that's something that not always present in most configuration management software. A lot of them will fail at runtime, and it may be interesting to try to catch errors before. That's what shifting problems left mean. That means getting the errors when you're building your policies and not when you're running them on production. Another important choice to make when you're implementing configuration resources is the return value, because you need some kind of a standard to be compatible, and so you require a kind of standard. So here is a very simple one, which matches the CF engine way, I would say, the original CF engine way with OK, repaired, and error states. And so when all your resources implement these three, one of these three outcomes, then the engine knows what happens and is able to react accordingly. Another question that is really interesting when designing resources is how far do we want to make things general? How far we want to have general interfaces? For example, do we want to try to make our resources multi-platform, or do we want very specific resources depending on the context? Do we want a package resource that will handle installing packages using apt, DNF, or even an MSI on Windows, for example, or do we want very specific interfaces? And this is an important decision, because being too specific will mean that the software will become hard to use, because we'll need to think about the right resource to use. But being too general will mean that you will lack some precision, usually, and you will not find, for example, all the apt options. If you have a general package resource, then you probably won't implement all the very specific apt options. So there's a trade-off here that you need to find between a very general resource that would have thousands of parameters and would try to cover everything, and more specific ones. Another very important debate in the configuration management space, agent versus agentless. But in this case, what's actually the difference? Well, if we look close enough, when we are running our configuration management software, there is always a kind of agent, because there is a program running on the system and doing stuff. So, well, that's maybe a temporary agent, but there is kind of an agent. So this doesn't change much. Actually, if you want to make a system with an agent, agentless, there is a very simple option. You connect over SSH, you copy the agent, you run it, and you remove it afterwards. And it works really well. And it is even possible that some configuration management products actually added an agentless mode to their software by just doing this. And people are happy because they now have an agentless configuration management tool. I don't know if it's better, but, well, customers want it. But so at low level, there is really no difference for the resources. Whatever the process calling the resources runs just temporarily or for long periods of time. So this is not actually a decision, and we can have resources that work either on an agent or agentless, in an agentless context. Now we'll get back at the engine, and we'll see at which point we want the engine to be interleaved with the resources. Should our resources be pretty general, or should they share some state with the engine, for example, which would allow more features but blur the lines between the layers and maybe make things harder to debug and make it harder to have an interface that allows external contributors to build resources, for example. So there's also a trade-off to find here. And linked to this, there's a very interesting question, which is how are resources connected? Can a resource send information to another one? If you install a package with apt, can you send the version to another resource or something like this? This sharing of state is also an important decision. There are all other types of connection between resources. For example, some tools will make automatic grouping for example, if you have a policy that installs 4 packages, then it will group them and only make one call to the package resource with the name of the 4 packages. In this case, the engine actually merged the calls to the resource. So this is a way of connecting the resources, and that's an important stuff to think about when implementing resources. Another very classic one is to wonder if a resource can trigger something in another one, if a package installation can trigger a service restart, for example, and how this works. How do the information goes from one layer to the other. And maybe the last one, but a very important one, is in which programming language will you implement the resources? Some software automation and configuration management tools policies are actually written in a programming language directly, and in this case you can just write everything, let's say, in Ruby. So you have the policies in Ruby, like in Chef, and you write your modules in Ruby. This is really good for like users that kind of like to write code, but we'll see that it also has some drawbacks. But it has a lot of flexibility because you can share information really easily between the resources and the engine. Or you can use a different programming language. So in case your software automation configuration management system uses a DSL or just a YAML data, for example, then you will need a language to implement the resources, which makes it harder to hack into the system, but also hides the complexity better. I'll continue with a side note about this programming language choice, because it's more important, even more important than it looks, I think. There are obviously some consequences, some technological consequences, some properties given by the programming language or the tech stack you will choose. For example, if you choose, let's say, to write C, it will be fast, it will be pretty portable, but it won't be beginner friendly. So you have some objective properties given by the tech stack, but there are also values and culture around the programming languages. And this will kind of attract different type of people. And so that's something you need to consider, because it will participate in shaping the community. If we take a few examples of languages using in infrastructure software, we have obviously C for CF Engine in the 90s. Then we have Puppet and Chef in Ruby, Ansible and SoulStack in Python, more recent stuff in Go or C++ or Rust. And these are very different languages that attract different kind of people, maybe. So, for example, Ruby is something more oriented towards people who like to develop. That's not an easy language. That language focusing some aesthetic and some conciseness, while Python is maybe seen as more beginner friendly. And so that maybe, I think a big part of the Ansible success is that it's really seen as something you can try to act on very easily with no prior knowledge. While, for example, in C, it's not the case, or even Ruby. And so this has an impact on your user base. If you have an automation software that requires development knowledge, then you will attract some SRE teams and people with this kind of background. But if you choose a simpler language or a data structure like YAML, then you may attract some more ops-oriented people who don't really like to develop. They may write some small Python scripts, but nothing more. So this will also shape the kind of community you will get. And in some cases, maybe a simpler, less powerful but simpler implementation can be easier because it will allow users to enter more easily. So that's really something to consider. What kind of people do you want to attract in your community? Do you want developers? Do you want system administrators who are not really used to developing with, let's say, object-oriented programming or functional programming or things like that? So that's something you need to consider, because if you write a software in Haskell, let's say, then that means your user won't be able to hack it. That may or may not be a problem. Now, let's say we don't want to write our own engine, because writing an engine is it's really hard. And let's say we want to just create a resource to manage something for an engine we already have. And in this case, we can, the different configuration management tools have different interfaces to extend the resources you can use. So there are extension APIs. Sometimes there are two versions. One that you can use through a programming language, so a programming interface, and one with a simple data version, often with less features. So for example, for Ansible, you have a Python library if you want to implement a module in Python, or you can just implement a module in any language with just JSON data. CF Engine also now has this kind of interface with basically a JSON protocol. So if you want to add a new resource type to CF Engine, you don't have to write C code with a very intricate interface, but you can write in any language and implement a simple interface. Here is an example of a call to apply something through a custom resource. So this is what is sent to the binary that implements the resource type. Okay, and it looks like this in the policies. So it's used just like a native. It's called promise type in CF Engine, but it's your custom type that you have implemented. Before getting more into the details of what we did in Rudder, I'll just give a few interesting facts about other configuration management tools that I find interesting. So let's start with MGMT. So this is the resource interface for MGMT, and it has a lot of interesting stuff, but one of them is the watch method, because that's really the core of the magic features of MGMT. Is that the resources are able to emit events that will be handled by the engine and will lead to immediate reaction when something happens to the resource. So let's say you have a resource which is a file, then it will listen to events through iNotify, and if something happens, it will send a notification and the engine will be able to react. So this is an example of a very specific feature that allows very interesting stuff. I'll talk very briefly about Jet. Jet it's now abandoned, but it was an attempt last year to build something like Ansible, but in Rust with more speed and reliability. One of the interesting choices it had was that the Unix shell, was the unique system interface used to configure stuff. So it was an agentless tool that would connect through SSH and run commands. And that was the only way to interact with the systems. So I find it quite interesting, given the evolution of configuration management tool, that we are still getting back to basically Unix shell. DSC on Windows. DSC 3.0 is currently in alpha. It means desired state configuration, and it's a configuration management tool built into Windows. And the new version is actually way more like our usual Puppet, Rudder, or others, because it's now multi-platform, open source, and resources can be written in any language. It's YAML based, so they are really getting into the configuration management that existed 10 years ago on Linux, but that's interesting to see. So what are we missing with all the current abilities that we have? Well, I think there's a problem with observability. The complexity grows, and we still get information about what happens in the configuration management tools through text logs, and it's really hard to get more information from these logs. They were made for debugging, to help system administrators debug the problems. But if you have a more global view and you want to see what happens on the infrastructure, then they're not really suitable, and you would need more structure output. And that's actually the hardest part when you implement a resource. If, let's say you implement an APT resource, that's not that hard, you just call a command. But then you need to handle all the failure modes, and you need to extract the information and return it in a structured way if you want people to be able to do things with it. And that's really what's hard in implementing a resource. There is also a problem of security traceability in the context of supply chain security threats. We really want to know what happens on the systems. For example, if we fix the permissions of a file, we really want to know what were the permissions before we fix them in a structured way that we can integrate, and not just in a human readable log file, because it's really hard to consume in, let's say, security grade tooling. So this is also important in security context to get better observability. Yeah. So some might think that immutability can be a solution to these problems. But the thing is, immutability is a model which has obvious qualities. But immutable does not improve observability magically, because immutable means frozen, but that does not mean we really understand what's going on. So it does not always help in this regard. And mutability also has some qualities. It's often faster, it's lighter. And if we make a parallel with programming languages, a lot of programming languages actually try to prevent mutability, to prevent all the bugs related to mutability. For example, a lot of functional programming languages did that. But it may not be the only way to handle mutability correctly. And for example, Rust aims at managing mutability instead of preventing it, because at the level of system software, we actually need something efficient, and we actually need mutability. And I think in some configuration management context, mutability can also be a quality and be something that we might want. So, in Rudder, now I will talk a bit more precisely about what we are currently doing in Rudder. So we have a Unix agent, which is actually a CF engine, an embedded CF engine agent. And we also have a custom Windows agent based on the native technologies like previous versions of DSC and PowerShell. And we want to be able to implement new resources, providing new features. We kind of believe in strong typing for rather in general, so we use Scala, Rust, Elm in the rest of the program. We look to keep some CF engine benefits like the performance and reliability. Our users, because of the way Rudder works, are usually not dev-oriented. They're mostly really ops, like people who want to manage system but not write too much software. So having a language that is accessible is not something we are focused on. And most importantly, we don't want a big bang. We want a slow transition towards these new features. So what did we choose? We chose to implement standalone resources, pluggable to our existing agents. We chose Rust as the implementation language because of these qualities of speed and reliability. And we obviously don't expect our ops users to write Rust, but that's not a problem. We might provide at some point a small Python API to do basic stuff, but our users actually want something that works. And we also have kind of simple resources for now, so nothing magic like MGMT. We mostly want to improve observability and security, and we don't want to provide like immediate reaction or event-based or nothing really magic like this. And so for this, we decided to use the extension interface of CF Engine that I presented just before, called custom promise types. This allows moving the complexity from the CF Engine DSL. We actually implemented a lot of resources-like stuff in CF Engine itself, but CF Engine is not suitable for programming. So this allows moving the complexity lower in the stack. And another interesting fact is that given the API is an arbitrary JSON, we are able to add another layer of abstraction between CF Engine and our resources, which allows these additional features. To make a small comparison, I don't know if you have heard about the Language Server Protocol, LSP, which is a standard for implementing IDE features for a language. So it comes from VS Code originally, but now it's present in almost all code editors or IDEs. And the principle is that you will, when you're writing a programming language, you will provide a binary that speaks standard API, which is JSON-based, and then any text editor will be able to plug to this, to call this binary and speak with it in JSON and get all IDE features like auto-completion, error detection, everything into your IDE with a single implementation, while before you had to implement it in every text editor. So that makes things easier for programming language authors. And I think it has kind of the same technical behavior. So that's an independent binary that just talks over std in, std out in JSON and allows plugging to different engines. So I think that's kind of an inspiration in our case, because we want to work with several different agents, but only implement it once. So it works a bit like this. I don't think it will become a standard because the economy and incentives are a bit different. It's really hard to implement an LSP. It's kind of easy to implement a resource in general. And there are much fewer configuration management software than text editors. So probably, I don't expect it to become a standard, but I think it's still a good idea. And we actually have a Rust library that allows to build these binaries that implement the extensions API of, let's say, CF Engine, Ansible, DSC, and the same implementation could be used as a custom resource in all of these tools. It also includes some static validation and YAML data as input with some additional static verification, because we want to be able to verify things statically quite early. So this is what the interface looks like. You might not like the Rust syntax, that's not a problem. But basically, the first method is important. It returns basically the description of the interface. So it gives all the parameters, the accepted values, the documentation, everything. And then we basically have a check apply that takes some parameters to and returns something which is either OK, repaired, or error. So that's a very simple interface, but it allows plugging to a lot of existing systems just with these simple methods. So that's currently exists and will be released later this year in Rudder. So we actually use this library, we implement the different methods, and then we build a binary that can be used by any of those of the agents. And the binary itself can output its spec as YAML. So this is quite flexible in its usage. Something I want to add at some point is some inventory features, because once we have this idea of centralizing, let's say, access to the package manager in one binary, then you may want to use it to get facts about your packages. So the inventory part could also come from this binary, and then the engine doesn't have to know anything about packages or services. And I would also like to add more structured output. Currently, it's only, given the constraints of CF engine and our existing Windows agent, it's only some text messages plus an outcome which is either OK, repaired, or error. But I really want to add more structure output, like diff if you modify the files, previous state of the resource when you modify something. There are some other perspectives in the check apply world. So we can think of NixOS, NixOps, Geeks, which are NixOps is a configuration management software for NixOS, which are Linux distributions that have a very specific model where you actually describe the state of the system you want, and it will be applied by the system, and it will guarantee that the system is in the correct state by design. But it's a bit harder to use, and I'm not sure it will get to the server space. For now, it's mostly a desktop distribution. So it's interesting, but hard to use, so I don't know what it will become. And for making, another option is to make things easier to manage. So, for example, drop a Linux kernel and just build very specialized binaries with, let's say, microkernels, where the configuration surface is very small, so the management is easier. Or a specialized system, let's say like Talos Linux, which is a distribution that has a very limited configuration surface from the outside. There is no SSH access, only an HTTP API, but it's only for very specialized use cases of hosting containers. Okay, so thank you. That's the end of the presentation. What I want to tell you now is that I think there is really some things to discover in the configuration management space, that it's not dead, that it's not over, that not everything has been found yet. And there are a lot of new needs that we will have around security, compliance, observability, and that we really need some new ideas to be able to tackle them, and have fun implementing stuff. I actually have a lot of fun implementing these resources. Thank you.